Right, morning everybody. Let's see if the technology works. Okay, so this is about a critical success factor. So what is one of those, you may ask? Something that the company is trying to achieve its goal. Manufacturing, one of them is probably productivity. Yeah. So this presentation is a very condensed version of what was produced 18 months ago. I will push through some slides if time is moving on, but I'll try and get as much done as I possibly can to give you a full overview of total productive maintenance. This symbol has been with me for 30 years, and it demonstrates that total productive maintenance involves everyone in an organization, not just maintenance. So some person called Peter Wilmot, he was quite well known in the 90s on TPM in the Western area of the world, UK mostly, and he defines TPM, as you can see, and that is a common theme in all other countries, especially Japan. So why not just call it maintenance? It doesn't embrace all manufacturing, and it's not just about fitters and electricians. It's about the entire organization. What are we trying to achieve? That's the first thing, what we're trying to do. We want more reliable equipment, less breakdowns, better performing equipment. That is in terms of running faster and also in terms of product quality. Reduce maintenance costs, improve maintenance staff efficiency, being able to predict when a failure is imminent, being able to prevent failures following predictions, and provide longevity to equipment by keeping it in good working condition, and bring maintenance and production close together with one common goal. What are the likely outcomes? Improved contribution to bottom line, more profit or less loss. Improve utilization of maintenance staff, lowers labor costs. Free up production capacity. Better engaged production engineering teams, eliminates infighting. Less scrap. Lower energy costs. Reduction of senior management stress. Improve on-time deliveries, helps win more business. So let's begin. How are we going to achieve this? Back in 1995, the first model I produced, and there was 8 steps to achieving the full total productive maintenance strategy. Systems, measurement, autonomous maintenance, housekeeping, continuous improvement, culture, training, plant design. It has evolved and includes more elements as TPM continues to grow, as technology is more with us than it was way back then. So let's look at inspection activity. You've got preventive maintenance by maintenance teams, predictive maintenance by predictive maintenance teams, and autonomous maintenance. And these are done by production operatives who have been developed with basic skills. Before you do anything though, you need to understand your machines. If you don't understand your machine, you can't set about trying to maintain it. So you need to understand where the data's coming from, information it's coming from, the levels of automation, failure modes. You need to know a lot about your machine before you can start to put together a preventive maintenance system. Some analysis of why the equipment has fallen over. Is it because of preventive maintenance and plant design, or lack of continuous improvement, repeating the same thing over and over again, the same problem? Autonomous maintenance is not there. And this is data that I collected many years ago, and you can see the percentages of what the root cause of components breaking, for example, was lack of preventive maintenance, or it was a plant design issue. You've probably seen preventive maintenance also called planned maintenance, also called scheduled maintenance. But basically, it is a program of maintenance scheduled inspections to increase plant availability and reliability. Should not be referred to as reactive maintenance, breakdown maintenance, running maintenance, essential maintenance, and critical maintenance. And if it's not broke, don't fix it maintenance. So, preventive maintenance, which is one theme of TPM, starts off with cleaning, intrusive checking, visual checking, measurements, adjustments, inspections, and replacements. When you walk around the factory, you walk around the plant, you've got 5 sensors. Although the taste one you might not wish to use, but sometimes you can taste the factory. So you've got listening, smelling, feeling. The plant is talking to you every time you walk around it. It's telling you stories. One method of recording schedules that ought to be done for things like walk around. This is an example of a customer, recent customer, where we're using the 5 sense symbols to define what needs to be done and some sort of prioritization, which we'll come to later on. How do we define what needs to be checked? You've got the OEM documentation that will detail what they think you should do. You've got your own experience of looking at new plant and equipment before it's actually installed and coming up with your own thoughts and ideas on what needs to be in a maintenance schedule. You've got breakdown history, corrective actions, statutory requirements for maintenance, and also health and safety, environmental. All part of what needs to be thought about when putting a system together. Whether it's paper-based or whether it's computerized, the same rules apply. Decide on what needs to be checked. Detail the work required and what is the schedule. And it's simple as that, putting the schedule together. Assigning priorities. Consider how the schedule would affect plant availability. If the plant needs to operate because you've got customers need parts, production aren't going to be too happy if you say you need 8 hours on maintenance. Consider special tools activity access and assign the 5S symbols. So we all recognize that. That's a bicycle, obviously, but for this example, really, let's imagine it's a machine. So we break down that machine into various elements. We put together a schedule. Okay. So for the bike itself, it's a function check. Does the wheel run true? It's a check. Spin fast, to check for movement. A priority, out of production. So if you are the mechanic of the race leader on the Tour de France, I'm sure he'll have something like that. And you'll see that some of those inspections is BR, it's a bike rider's responsibility, autonomous maintenance. And some of it's the mechanic. This is how your schedules become developed. Some can be done whilst he's riding the bike, and some can't be done whilst he's riding the bike. And that's where you've got out of production and during production. We'll talk about this later as we move along. And if you're looking at a piece of equipment and you're walking around it, have your schedule side by side as you're developing, and so you understand and you can piece it all together. And one small, well, that bicycle, for example, you've probably got 50 inspections on that alone. Suzuki model, which I use quite a lot on defining A, B, and C prioritization. It's a very simple model that defines the worst case scenario to will it really matter at the end if it falls over, and the cost of failure. Health and safety, always a priority. Environmental, always a priority. Quality, always a priority. And depending on the criticality of the machine, if it's a core machine, you've got 20, less critical than if you've got one mold in line and that falls over, the whole factory's not operational. And we move on to predictive maintenance. And that means looking at your equipment, testing the equipment without stopping the equipment. It has to be operational under predictive maintenance rules. And what you're looking for, shock pulse monitoring or bearing analysis for conveyors, drives, vibration analysis on fan sets, oil debris analysis, hydraulic oils, gearbox oils, transformer oils, thermography on your switch gear, your high voltage switch gear, the LV switch gear, your lighting levels in the factory, local exhaust ventilation, and even water conductivity where you're operating medium frequency induction furnaces as an example. How to start? Detail what needs to be checked whilst the plant is running. Find the right equipment for those tasks. Train dedicated staff. Add checks to the master PM system. Operate from I would call laboratory style environment. Everything's got to be clean, well looked after. You're taking hydraulic oils into the testing area. You don't want contamination to give you a false result. It's the mindset that predictive maintenance is going to perform extremely well done correctly and keep the plant running, and also be able to predict when something needs to be done before you get what I'll call a major. I call them found industry standard requirements, what I would expect to be done with condition monitoring. That will be sand mixers. The sand mixers, if you have a sand mixer go down, it's usually bad news. So a bearing that is not monitored and falls over can cause catastrophic failure of other components within that mixer. Huge downtime, huge cost. Conveyor belts, extraction fans, air compressors. So you consider what is critical plant. Hydraulic oils, proportional control valves for movements, critical movements of your plant and equipment, whether it's a core machine, whether it's a molding machine, whatever it might be. Proportional control valves need clean oil, and I mean really clean oil. And thermal checks for electrical equipment, using anything from simple tool to the more sophisticated tools to try to highlight where you've got some problems with your circuit breakers or motor contacts that's going to lead to a failure. And it can be done very simplistically, and you don't need a lot of engineering qualifications to do that, provided you know exactly, you're not actually touching anything, you're just pointing a camera on the outside of a circuit breaker, and if one part of it is very hot in comparison to the rest, you know you could be in trouble in 1 month, 2 months, or even a year. So a few examples, these dating back quite a while. So some pictures I maintained on the system. And that's analysing a motor bearing on a big fan set. That data is downloaded onto the system. There are more intelligent sensors now where you can do this remotely. And if you've got critical equipment such as that fan set, then having transducer monitoring is far better than a snapshot. But a snapshot is better than nothing. As I mentioned, oil debris analysis, gearboxes, hydraulic systems, HV transformers. The local company in this area, they operate nationally. One example of where you can get equipment from. I have got a testing kit in the refreshments room. If you can have a look at, if anybody's interested. Just promoting this as a friend of mine, but it's just a typical example. You can go on the internet. There's many examples of equipment where you can purchase to test your hydraulic oil, your gearbox oils, etc. This is multi-axis vibration monitoring checking on that particular die grinder to make sure that you're recording your vibration on your handheld equipment for vibration VWF and making sure that you are maintaining the parameters that you're allowed to operate at. And if you're not, instruments like that will show that you are going to be out of vibration levels and the bearings need replacing or the unit needs scrapping. Just giving you one example of vibration monitoring. From a simple tool to sophisticated tools, again, you're checking some the main features of an electrical control panel. Water conductivity, I wouldn't recommend using the one on the left because the one on the right is far more sophisticated. But certainly on medium frequency induction furnaces, if you don't keep your water conductivity low, then you'll be causing yourself some problems with electrolysis and damaging heat sinks and chills and things like this that are required to cool the inside of an inverter. You need almost pure water. Testing it once in a while is a good idea. Local exhaust ventilation is a statutory requirement, as everyone in engineering will know, which is part of predictive maintenance. And checking lighting levels, for example. They will deteriorate over time and no one really notices until somebody falls over something and someone will come along with a light meter and say, well, lighting's rubbish. Well, you can predict it's going to be rubbish because you're going to see it falling away over time. So moving on to autonomous maintenance. So basically we wanted to try and get operators involved in maintaining the plant, the low level stuff. And why would we do that? Well, we would do that for the simple reason that you don't see it quite so often these days with guys on a Sunday morning underneath the car changing the clutch. But it did happen. And so with very little knowledge, you can clean the car. Then you can find defects. You know, the alloys have been scrubbed. Who was the last one to use the car, for example? You're checking your fluids, your oil, your water, checking your tyre pressures, you're checking your tyres for wear, all low-level stuff. But this is the sort of stuff you've got inside your factories. But everyone thinks it's a fitter or maintenance engineer's job to make sure that your tyre pressures are okay and your tyres aren't worn. It's not. It's part of what they call autonomous maintenance. And with skill shortages, let's think about upskilling production operatives, because we know with some training, if it was a car, you could be changing the springs and dampers, brake pads, exhaust system, the clutch even. So this is why I think autonomous maintenance is a very good thing in production environment. How long have I been involved in autonomous maintenance? That was produced by me in 1995. And those people there were responsible for checking the plant with the specific reference numbers. They knew exactly what to check, whether it's weekly or monthly. So autonomous maintenance, I know, has been practiced at William Lee before 1995. And it still continues, Matt. So data analysis. What gets measured gets done, as I say. So TPM is looking at mean time between failures. How often does it break down, the plant, and for how long? Quite important 2 bits of information. Tells you where you're going, and you get an engineering efficiency out of that. And what are the repair costs against production tons? And total works engineering costs against turnover. I implemented TPM at William Lee many years ago, and the costs were, comparison to sister company, better, and performance was better. So I was engaged to help sister company implement TPM, and in the first year save something like £350,000 on repair costs in year one, and maintain that. Other KPIs could be preventive maintenance efficiencies, in terms of schedules, corrective actions. We'll go on to sort of root cause analysis later on, and how long it takes to complete corrective actions, and the works engineering labour strength against total workforce. Very simplistic method, and again, this is very old, but it's still used today, recording all downtime, when it occurred, how long, gives you some statistics. Never be frightened of writing down the bare, the solid truth about what's gone wrong, vitally important, and get it. It's not a competition. You know, the worse it is, the greater the opportunity. So, as you can see, for the example for William Lee, their repair costs collapsed with the implementation of TPM. And it's remarkable. And I think they're still under the 1993's expenditure, even now. Works engineering costs, a total, which includes labour, contract labour, and engineering spend, also fell. What about the plant? From failing every 20 or so hours, it's now only failing every 50, 60 hours. That's the data. This is how far back it goes, just give you some history of what it can do. And every minute is recorded. It's not recording a breakdown every 10 hours for a 10-hour breakdown. It's every minute it's broken down, and that's mean time between failures. Maintenance labour strength fell. So data is important, and the right data is important. On housekeeping, we're going to skip through this fairly quickly on the basis that going through the full 5S is a day's job anyway on its own. But you've got basic 5S, which includes safety, workshop management and spares. And anybody who's seen anything about 5S will recognise that you're trying to sort out the shop floor and make it professional, tidy, operationally effective, so that you move from that to that very simplistically, and then maintaining that. And although it doesn't mean that the previous slide, that garage wasn't more effective as a business, I'm sure your customers will think this one is more effective. Some statistics from 2020, 2021, that by improving the shop floor in terms of 5S, it's going to help with what the biggest areas of injuries reported to the factory inspector: slips, trips and falls. So though we're talking about TPM, it will help with health and safety. And workshop management. If you read some of that list, you probably recognise many examples of where they can't find things. Who had the chain blocks last? Nobody put them away. Where's oxyacetylene? Hidden behind a conveyor somewhere. Leads to extended breakdown time, all part of TPM. Spare parts management. Again, it's a topic all on its own. But managing your spares, recording your spares, reordering your spares, having the correct spares, is all part of TPM, not to be taken for granted. So if the schedule maintenance side of it, and what you've just previously seen, is sort of the backbone, then maybe the brains is continuous improvement. 3-step approach I use. I use a typical 5Y system, moving to cause and effect, and then Kaizen if we've not got there. So the 5Y, it's a pretty standard tool. It's not designed by me. It's ask the 5 times why. You should come to the answers to why it's failed and what you're going to do about it. And probably that's a completed one, and goes through the step-by-step process of asking the same question: why, until you come to the root cause. Then you put in the actions you're going to take to eliminate. And it's important that these things can be overwhelming if you try to manage too much data all in one go. So anyone who's not doing 5Y systems, start with the more critical. As you get through them, you'll then become accustomed to how they effectively work, and your root cause and your corrective actions obviously are paramount. Sometimes brainstorm is quite helpful with the team. So brainstorming tool, again, you know, the common tools that probably most of you in this room are aware of, but it can be quite effective to trying to identify what could be the cause of a problem. And for motor burning out, you can see quite a lot has to be thought about with potential possibilities of what might be causing the problem. With Kaizen, I look at the individual orientated Kaizen. If a problem cannot be solved, you have to get it back onto the shop floor and do shop floor studies. And you record everything that you're doing, as much information as possible. You take it back onto the shop floor, involve more people if you need to, but you need to take it back on the shop floor and fact find. And that's a simple tool that I've used in the past. Moving on to plant design and component failure analysis. We need built-in reliability, easy maintenance access, standardization of parts, and replacement component critical assessments. A basic model of a before and after situation. So that's a model I've produced quite a while ago. Original breakdown stoppage time, minimize stoppage time, and there's that model there will take you on that journey. Very quick example again of replacing a dome valve seal on a molding machine, original task time, and redesign, much lower time. Same with, again, a molding machine, level probe. The original time, 48 minutes, was reduced down to 4 to 5 minutes. Backup systems, dual standby operational systems. And defect tagging. As you're walking around, you find problems, you can't get to do anything about it, you tag it. And then you carry out an assessment to try and find the root cause of that particular valve or whatever it might be, to try and get the root cause of component failure. I feel like I'm flying through these slides at the moment. I'm just conscious of time. Like I say, this is a full day training workshop, which are condensed very quickly. Well, let's have a look at some visual management. So gauge painting, valve marking, defect tagging, match marking, color coding, shadow boards. Match marking. Two things, in my opinion, why they are so effective is, one is that once you've tightened something to the correct tightness setting and you mark it, you're more likely to have done it if you marked it than if you didn't mark it. And also that if you are checking bolts for tightness, you don't need a spanner. You just look to see if the lines are, if the marks are lined up, the bolts are tight. Simple as that. If anyone's doing maintenance schedules and keeps checking the tightness of those, eventually they'll just over tighten them and stretch the threads, and they're all good. So visual management there. This is an example at Amiga OEM, where they've match marked theirs from scratch. So they've assembled it and they've already done that. During operational use, after a few weeks, the markings probably need to come off, retorqued and reset. But it just shows you that the OEMs are also including bolt match marking and defect tagging, as mentioned earlier. Color coding pipe work. So you can have a feed and return system on pipes. So in a hurry, you've got a water leak, you don't know which is a feed, which is a return. Color code, match your blues, match your yellows. Simple. Gauge painting. You don't need to be an engineer to know whether the oil's hot or not. You just need to be on your walk around and seeing and looking, and sees it in red, you speak to engineering, the probably cooling's probably fallen over. Marking valves, should they be open or should they be closed? This is a manifold which has got many different pressure setting requirements. This is marking up, now marked up, and you can see that the gauges are painted, you've got labels on valves, and it looks more professional, and it helps the operator when he's walking past his equipment. If he sees something in the red, he can report it. Simple techniques, take no time at all, and often you find faults whilst you're doing this process. And marking valves, as I said, some are open, some are closed. When you're in a rush, you've got a problem, nobody will remember whether that valve was open or not, but with a tag on it, you will. So review, where do we start? Tracking the 6 big losses, setting up preventive maintenance, improving equipment reliability, autonomous maintenance, or pull it all together. Highest influence and the cost benefit comparison. Predictive maintenance will give you the best return on cost basis, cost benefit basis. Preventive maintenance, problem solving. Numbers involved in each critical success. Preventive maintenance needs a lot more people than predictive maintenance, but as you can see, that's the numbers involved, literal personnel involved in doing the full TPM system, and the effort required. And problem solving, my experience, it's the biggest single requirement that needs the most effort to keep going. People tend to drop off things like problem solving after a while. They do it for 2 or 3 months, and then they get fed up of doing the same thing over and over again. Problem solving needs a lot of effort. It needs to be part of the culture. You have problems, you have downtime, you have a fault, you fix it, then you analyze it, and you eliminate it. And if you don't, you're going to keep going around the circles. Predictive maintenance doesn't need a lot of effort, neither does preventive maintenance. It should be in the system. You've got engineers on site, you've got a system, you should be okay. But problem solving is usually the biggest one, that because it's a process that's done after the event, sometimes after the event ones, which are vital for the future, get left behind. So thoughts take back. Methodology, it has many steps, and we've literally skimmed through a huge TPM strategy. But steps are clear and simple. It's not that difficult. A lot of it is so common sense-wise that I'm still amazed when I visit places and they've got no maintenance. It's not just about engineering. Everyone can be involved, everyone. Start with easy wins. Start slowly, build confidence. Don't get overwhelmed. Maybe just take one element of TPM a year. And that way, maybe in 30 years' time, you'll still be practicing TPM. Seek guidance if needed. And it's really a friend, TPM. Certainly been a friend for the companies I've been involved with. And of course, sales pitch at the end, if you need any help, call me. That's it. Thank you.
Thanks, Tony. I'm sure that's a lot for people to take back with them, and a wish list for your own maintenance department. If anybody's got any questions, I've got to pass you the mic so that the people sitting at home can hear. Is that a question, Richard? Sorry, thought you were bidding on the auction. Anyone else? Or like you said, Tony, always available. Contact him, and he'll come in and speak to your guys. Sorry.
It's okay, I don't think mine. It's an observation. I saw TPM use a company called Woolpack in the States. We've got 8 diesels, and one of the benefits I noticed was increased capacity, and they're able to operate their plant 12 days out of 14, 3 shifts. One of the things they did do is, besides what you mentioned, was they would take a failure, a major breakdown failure, and use that as a route to make it positive by doing, let's say they lost the autocore or whatever, they would then do mass blitz the diesels for routine maintenance, changing valves, whatever. Is that something that you would do in a TPM system?
I think I know what you're asking. So, start again. I think I know what you're asking on that question. If you have you got multiple plants that are copied, then it will clearly make sense that if you've had a failure on one, you put in the same maintenance schedules for all the others. So if you've got 10 core machines and you've had a failure on one of the core machines, you've found the root cause, you've carried out corrective action and implemented it, you must do it on all the others. Yes. Oh, yeah. So basically, if you've got a breakdown, for example, you use that opportunity to carry out autonomous maintenance, or absolutely, yeah, yes. But they have to be switched on, because often, in my experience, if a plant does break down, then often there's not a lot done for the first 30 minutes, maybe, and you know, it needs to be organised, that, because you're not planning for a breakdown, so you're also not planning to be jumping in to do the scheduled maintenance. So it really needs to be understood by the organisation that in a circumstance where something's broken down and it's going to be down 1 hour, certain people know exactly what they need to do. And that could be, say, right, I need to do this check, that check, that check. That's, yeah, definitely part of what TPM is all about.
Stuff, guys. Sorry, Awais? Yeah, just a minute. Yeah, it's for people at home, sitting at home. Yeah,
Tony, just a quick question from me. TPM, can it be applied by your internal production maintenance or the supplier of your equipment? Who should it be applied by?
Right. So, in my opinion, the organisation knows their equipment more than the OEM when they've operated it for a while. They get the experience, they understand it. I've seen many OEM manuals that barely skim on the surface of what's required. So in terms of TPM, you do it yourself. Whatever level you want to do it to, you do it yourself. Because if you don't, you can bring in some fancy consultant like me, then walks away, and you'll just drop it just like that. You need to do it yourself. I can guide, but you need to do it yourself and not bring in an external, in my opinion. Does that answer your question? I'm not quite sure whether I have.